Hello everyone, welcome to this lecture on today the transport layer, which will be the topic of the next lab. The transport layer in TCP/IP is TCP, hence the name TCP/IP, and UDP. We'll see most of it today. Let's start with first a reminder. We've seen this already in the first week, but let me recall it. The main goal of the transport layer is to make the network, available to programmers. So in lab 3 you will be a programmer. You will use the network to do some things, and the way to use the network is via the transport layer. The transport layer is in principle only in end systems. We will see a few examples where you might have the transport layer in between. Then it's called a transport layer intermediate system. But in principle, it's not the intention of the TCP/IP architecture is that the transport layer is only in end systems. There are two transport layers in TCP. They are called TCP and UDP. UDP is the simplest, and if you want, is the bare-bone transport layer. And TCP adds to UDP essentially two functions, error recovery and flow control, plus a third one, which is called congestion control. That we will see later, because it is not a transport layer function, even though it is implemented in TCP. First thing to realize is there is no TCP v6. There is no UDP v6. That's the good news. At the layer above the network layer, like at the layers below, there is not a MAC v6 or a MAX v4. There is only IPv4 and IPv6. TCP is the same, whether you use v4 or v6. The protocol is the same. However, the service interface is different. So if you use the network over TCP using IPv6, you will use a different interface than if you use the network over TCP and over IPv4. This is because since the format of addresses is different, you need a different interface. And as we will see, most operating systems, in fact all that I know of today, view the two as separate. But from a protocol viewpoint, they are exactly the same. So we need to learn it only once. Let's dive into UDP. UDP is very simple. The only thing it does is essentially introducing port numbers, which we've already encountered. So let's have perhaps a more final discussion on this. The idea of port numbers is simply that on one process, there is typically, on one machine, reachable by one IP address, there is typically more than one thing that you speak to. If there would be only one thing that you speak to, we would not need port numbers. But practically all machines have a large number of things that you would like to speak to. And how do you speak? So those are illustrated here by different processes. There might be inside a process different functions that are used. But typically you have different processes. And one of them, this one for example, is a DNS server. On the left we have a machine which is perhaps a PC. When the PC talks to a DNS server in order to do typically name resolution, it uses UDP, and it will send a UDP packet to the DNS server on this machine. Now on this machine there are other things. You might do Skype on this machine, although it's probably bad taste to do Skype on a DNS server, but it's not physically impossible. And you might have another of other services that are running, network, time, and all possible things that have been invented. Yes, question?
Yes, the router or something that does the NAT translation acts as it uses ports. It is on the transport layer then.
So the question is, since a NAT looks at port numbers, it is a transport layer box. Perhaps, well, this is terminology, so terminology can be like religion. You can fight to know is this or that. Frankly, I don't know. A NAT, again, is a hack. So a NAT violates the architecture. So since it violates it, it's hard to place somewhere. And we will find a number of them, of those things that violate the architecture. But it's easier to understand networking if you know what is in the architecture and what is violating it. So a NAT is a packet forwarding devices that does a deeper packet inspection that would be strictly necessary if it would be a router. But it does only packet inspection. It doesn't really understand the thing, the transport protocol. For UDP, there is nothing to understand, so, okay? But for TCP, there are things to understand. For example, in TCP, we will see if a packet is lost, it will be retransmitted. A NAT doesn't care about that, although a NAT will see whether a packet is lost if it looks at the sequence number. But typically, it doesn't care. Here, I'm showing two port numbers, the port 53 on the right and the port 1267. Ports like 53, the ports below 2 to the power 1000, typically are reserved ports that are defined by standards, by the IETF, the Internet Engineering Task Force, and are so-called well-known. They are typically the ports that are used by servers. A server is a machine that listens for requests to arrive. A DNS server is a server. It's waiting for DNS requests to be handled. If you want to speak to a server, you need to know its port number. If you want to speak to anyone, you need to know its port number. But typically, if you have what is called a client-server interaction, meaning one of the two devices is running and listening with a process that typically runs in the background, then this one needs to have a well-known port number. The other, the client, does not, because when this machine A will speak to B, it will send a UDP packet called a UDP datagram. Of course, inside the UDP datagram, there will be the source port number, which is here, 1267. It will be written here. So since it's written in the packet, the server doesn't need to know in advance which one it is. It's like when you receive a postcard and you want to reply, and if the reply address is written in the left of the postcard, you know whom to respond to. So this is how UDP ports are used. TCP is the same. Now you can have several processes on the machine that are talking to the same DNS server. For example, if you have this PC, you can open one internet web browser and another completely different Google Chrome or Opera web browser or even Safari. Then each of them will probably use their own, because they are not using any software in common. They will probably, each of them, have their DNS resolver function. So each of them will contact perhaps the same DNS server, perhaps another one. So you might have different ports also on the client side. What identifies a flow of communication is the combination of IP addresses and ports. So it is perfectly possible to have several flows of communication to the same port number, here 53. But you cannot have both 1267 on host A and 53 on host B for two different flows. So the IP addresses and the port numbers uniquely identify a flow. That's, I would say, the major concept of UDP and TCP in terms of addressing. All the rest is minor details. In a UDP packet, you have a few other things, essentially the message length and a checksum. The checksum is an attempt to do some error detection with a very weak, actually, checksum. It uses modulo 2 to the power 16 minus 1, so complement to 1 arithmetic, which those of you who had information theory know we can do better with cyclic redundancy checksums or Reed-Solomon codes. But here it's historically driven. Sometimes machines do not do the checksum. If you don't do the checksum, you put 0. Again, we find this convention. Absence of a field is 0. Sometimes servers don't do the checksum because doing a checksum requires some CPU time. If you do a benchmark on server A versus server B, if server A doesn't do the checksum, probably it's faster. It can handle more messages per second. So sometimes people play those tricks. The UDP service is very simple in the sense that it is message-oriented. So I'm now talking the view that the programmer, that you in Lab 3 will have of UDP. Message-oriented means when I write into a UDP socket, I write one chunk of data, which is called a message. So the service data unit is called a message, that has a maximum size. It cannot be more in principle than 64K, 65,000 bytes. And then the UDP semantic says, I will take this message and try to send it to the destination. And then, with very high probability, covered by the checksum, either nothing will be delivered or all. Right? So it's like a big packet that you give to the post office. Then the post office usually transmits it, sometimes loses it, but it's very rare that it cuts it into two and delivers only one half of it. Right? In the internet, it could happen, a block of data could be split into packets, but UDP says, no, I will always transmit the entire message that you've passed to my interface. That's the first thing. If the message is too large, for example, if it's more than 1500 bytes over a machine that uses Ethernet, it will be broken by the operating system that implements UDP into several IP packets. But at the destination, UDP will wait until all the packets are received to deliver it to the receiving end. Question?
Does it do a retransmission, or it just wait
No.
until a timeout? And
UDP does not do retransmission. It just waits if all the data has arrived. If it has not, then it will kill the packet. As we will talk later, it's a bad idea to rely on this. When you send data over the internet, you should make sure it is not fragmented. It is not broken into pieces by UDP, because if it's broken into 3 pieces and 1 piece is missing, UDP will declare the 3 lost, which is not efficient. So the application will not see that 2 out of 3 have arrived. Right? Because the application uses the UDP interface, which is message-oriented, so it delivers an entire message, not piece of a message. Right? Why is it like this? Well, it is because it has a positive side effect. The benefit of this is that you don't have to bother about framing the data. An application sends data, but the data at the end of the day is just bits, zeros and ones. So when an application receives the data, you need to know where is the beginning and the end of something. Take, for example, a simple example where you write in C a character string. A character string in C has the peculiarity that it has to terminate with a 0, with a null byte, right? Which is one convention used in C. Assume now you send this over a network. You send the bits and bytes, then you have to make sure you receive the entire character string. If you receive just half of it, then it's not a valid character string because it doesn't finish with a 0. Right? So your system will crash if you send it half a character string. With UDP, you don't need to bother. If an application writes 1 character string into a UDP socket and the receiving end receives the character string, it knows it will receive exactly what has been sent. It may receive nothing. It has to be handled by the application, but it receives something, it's the complete character string. As opposed to TCP. TCP does not do this, as we will see in a minute. That's the essential difference. Here is a typical use of UDP. You can use UDP in a variety of ways. The bare bone way of using it is called the socket library. The socket library was a library that was invented in Unix, but has been since then used in all operating systems. It's a set of system calls that directly use UDP or TCP. It's fairly rare to use it other than in Lab 3. Usually you use higher level libraries that themselves use sockets. So particularly if you use Java rather than C or Python, you will typically use more elaborate constructs that will use the sockets. But it's good once in your life to use the sockets because all the bizarre things, all the peculiarities of the sockets are somehow visible at the higher levels, even if you do more concrete, more abstract primitives. Here is how a client and a server might communicate with TCP. For example, this is a very simple program that sends 1 string of character to another one. One of them has to be a server, because there is no other way of using TCP and UDP today. Even if you have something that says beyond client server paradigm, blah, blah, if it will still be a client and a server somewhere. Peer-to-peer means that you're both a client and a server. Now, a server versus client is a role in an interaction. Right? So things can be very complex. You can have a complex program that sometimes takes the role of a client, sometimes the role of a server. Of course, some machines, some programs like a DNS server is most of the time taking the role of a UDP server. That's why we call it a server. But we shouldn't be fooled by this distinction, again, between product names and architecture. Here, a server means that it listens. And listens in UDP is done simply, so you need to do a few management things, like before using a socket, you need to create the object, which is like creating a file descriptor. Before writing or reading from a file in any operating system or any language, you need first to create in your environment a file descriptor that gives the necessary bells and whistles for the operating system to allow you to read and write from the file. Sending or receiving from sockets is intentionally done the same as writing or reading to a file. That's to keep things simple. So you create a socket which returns typically an error code if creating the socket doesn't work, and typically also involves a number of attributes. For example, you say whether it's an IPv4 or IPv6 socket. Even though UDP is the same for both, the sockets are not the same. So you create one or the other. Those two sockets are different. They are treated differently by the operating system. Then you bind the socket. Binding the socket means, in principle, giving the IP address, but most of the time it's done by default. Typically, a machine has rules to know which IP address to associate to itself. For example, most machines will give priority. Most machines have one Ethernet, one Wi-Fi, perhaps a few USB interfaces. Then you give priority to Ethernet, then to Wi-Fi, then to USB, typically. But you can decide to bind the socket to a given IP address. But the most important thing is to bind it to a port number. You can do it in two ways. If you're a server, you explicitly give the port number. So you say, now I am a socket, and I bind to port 53. In order to bind to port 53, you will need to have privileges, depending on the operating system. In most machines, you will need to be a super user to be able to do that, because all those ports, the reserved ports, are not usable for ordinary user programs, but only to privileged ones. Then once you've done that, you're ready to receive. So this very simple program does a receive. Now it's called a receive from. Receive from means I'm listening, I'm ready to receive a message, and I can receive it from anybody. And because I'm receiving from anybody, I need to know from whom it is coming. So the receive from will return a message as soon as one message has arrived. Plus it will return the IP source address and the port source, the source port number. This is typically what a DNS server will do. You can do what is called connect a socket. If you use UDP and you want to receive data only from one specific machine. For example, if you're opening a Skype session and you use UDP for that, then you don't want anybody to send you data, and you've had already a handshake with the Skype service of some kind, in that case, you can connect a UDP socket, which simply means restrict it to receiving data from a given source, IP and port numbers. If you do this, then you will not do a receive from, you will just do a receive or a read statement, because you know everything that arrives must come from the thing that you've connected to. On the client side, you will do similarly, open a socket. You will bind, except here the bind will not pass as argument a port number, or it will pass 0. And then it will receive, as a result, as a return value of the call, it will receive something that indicates whether a port number was allocated, and if so, which one it is. So the goal of bind here is to ask the operating system to give me the next available port number, which in principle we don't care. It's for us a random number. And once you've done that, well, you can send some data. And if you send once you've completed the send, similarly you do a send to if the socket is not connected. And once that happens, that will send the data to the server. If the data is not lost, the server will receive it. What happens at the server if it does the receive from before the client doing the send to, which is the typical case? By default, it will block. So the receive from will be a blocking call. You call the operating system, and then the program that does that blocks. It doesn't continue execution. If you want the thing to continue execution, you need to do other things that you will discover in the lab. But the primary intention is to block. The send to, in contrast, doesn't block. The send to, well, it can block a bit if the operating system is busy, but in principle, it returns very quickly. Of course, this is a very stupid and simple program. It sends one piece of data and then sends it again, as we see here. It may very well happen that the data is lost, in which case this program will not know because there is no communication in the reverse direction, which is again a very rare case. I mentioned the case of airport display, which may use systems like this. So that might be the server might be the display, and the client here might be the source of information with the flight information. But most of the time, the server, after receiving, will analyze the data and will send data back to the source, of course. But I don't show this here to keep things simple. As I mentioned, there is no UDP v6, but there are UDP v4 and UDP v6 socket. So in particular, if you write an application program today, you'll have to choose. You'll have to choose whether to use IPv6 or IPv4, or if you have a smart library, you might use a high-level primitive that will send to IPv4 or IPv6 depending on what is needed. But this will be a library that encapsulates the sockets, that wraps around the sockets and adds another layer. How do we know whether IPv6 or IPv4 should be used? In principle, using DNS. You connect to a service or to some machine by finding its name, although you can connect directly to the address. If you have an IPv4 address, then you connect using IPv4. If you have an IPv6, you use IPv6. If you have a DNS name, then it's more interesting. You can use both. So you go to DNS and you ask, is there an IPv6 address for this animal? Is there an IPv4? If there's only an IPv6 address, you know what to do. If there's only an IPv4, you also know what to do. If there are both, then you have a problem. Which one should you do? In principle, in theory, you should use the newest. So you use IPv6. So most systems today, certainly the case of Windows and Mac, will use IPv6 if both are available. Although sometimes it's a bad idea because sometimes both services are available, but IPv6 is just here for the sake of being able to say we do IPv6. That's the EPFL case, right? EPFL is a pure IPv4 infrastructure where all services are made for IPv4. Now, if you go to a web server of EPFL, we have a few. In the lab, we have lca.epfl.ch, which we have made just for this course, just to be able to show the IPv6 logo. And that's true of all other cases. So all other servers are usually an intermediate system that runs on IPv6 and then simply points you back to the IPv4 system. So if you use IPv6, then it means you will always go through an additional intermediate system, which will delay, will give less good performance. So that's one of the tragedies of IPv6, that if you have both, probably using IPv6 is less good in environments like Switzerland, where IPv4 is the default entity. There might be places in the world where IPv6 is more important than IPv4, in which case it would be different. It's important, even though we don't touch the operating system, but it's important to have a mental model of what happens in the operating system, whether it's in software or even if it's an embedded device. They will all tend to do the same thing. So mentally, here is what happens when we use UDP. I have an application program that is connected to, for example, here, 3 sockets, or different programs that use 3 sockets. What the programmer will view the socket number here, 345. This is what is returned by the socket call. It's a file descriptor, in fact. It's like if you open a program that writes into a file, you will have a file descriptor, which is a small integer. It's not the name of the file, it's just the local number you use to know where to write or read things from. Now this program has opened 2 IPv4 sockets and 1 IPv6 socket. Then when it sends data, they are put in the IPv4 socket buffer and they are immediately sent. It's more interesting to understand what happens when data arrives. So when an IPv4 packet arrives, for example, when a packet arrives, the operating system knows from the Ethernet hardware or Wi-Fi whether it's IPv4 or IPv6. So it's immediately switched on the IPv4 stack or the IPv6 stack of the machine. If it's IPv4, the operating system will check whether the IP destination address is one of the addresses of this machine. And if so, it will continue and do the UDP processing that will read the destination ports. Here, I'm showing different destination ports. Here there are 2 ports that are the same. And there is 1 port which is different. It's intentional because here I have an IPv4 socket and here an IPv6 socket. In principle, the different sockets will have different port numbers, although it's also possible to have several sockets in the same port number, but in principle, only if you do complicated stuff. So here, if a packet arrives, by analyzing the port number, we know essentially what we are doing with this packet. For example, in Skype, is it a voice packet or is it a control packet? Control means in Skype you're sending a request to close the connection, to add a third party. Things like this are typically sent to a different port numbers than the voice, because they will be handled by different pieces of software. So this will be then put in 1 buffer per socket, and then the operating system buffer is what is visible indirectly when you do a receive or receive from call on the socket. When the application does a receive, what happens? The operating system goes into the buffer, see if there is something. If there is 1 message, it will pass it to the call of the application and destroy it from the buffer. By default, there are zillions of flags where you can change the behavior, but in principle, when you give the data to one application, the data is consumed, so you remove it from the buffer. Now I'm showing another packet that it has an IPv6 format, an IPv6 destination address in particular, and here the same port number, it's the same UDP port, but since it's IPv6, it's a different machine, logically, so a different process also, and then a different socket that will use it. Right. So this is how things are for UDP. Now a small question. So the machines we've seen a minute ago are perhaps Lisa's browser that's trying to access a web server, but in order to access a web server, it needs to translate a DNS name into an IP address. This is sent over UDP. Messages can exceptionally or less exceptionally be lost in the internet. What happens if the query or the response to the query, the answer packet, is lost? I propose 2 solutions, and perhaps none of them is true. What do you think? I close in 5 seconds. correct answer is the majority. The name resolver has to implement reliability, and the simple way to do it is the stop and go protocol. You send a query, you expect a response to your query. That's why you send a query. So if no response, so you don't need to ask for a specific acknowledgement because you expect an answer to come. If nothing comes, after some timeout, so you need to have a timer in the DNS client, then you'll send again. In fact, it's a bit more complicated. You'll send again, but you'll also increase the timer so that you don't keep sending queries, and you send again a number of times, typically 3 or 4 times, not more. Question?
Haven't we said that UDP does not resend packets?
Yes, UDP. It's not UDP that resends. It's the application program. So in lab 3, if you are writing the program, you have to make a loop that says send until you get free from sending, until a maximum number of attempts have been done or not. So all the complexity of sending and resending and verifying whether an acknowledgement has come and deciding whether to continue to try again and computing timers, all of that is done by the application program in UDP. At least if you send messages and queries. There are other uses of UDP that may not like to resend. Can you think of one? Skype, typically voice audio signals. You will try to have a smarter coding scheme where if a packet is lost and if you care a lot about delay, you will try to hide the loss by doing an interpolation from the previously received packet, for example. So some applications might prefer to do their own thing rather than be sure to receive exactly the ACK or be sure to receive all the data without loss, in which case they use UDP. But again, there will be a complexity at the application level of hiding all the losses. And if the loss rates become too large, I mean, this won't work, right? So you might still want to recover from losses. Well, that's exactly my transition to TCP. If you care about losses and you don't want to do what the DNS client has to do, then use TCP. TCP will do it for you. So TCP was invented exactly based on the observation that many applications will do the same thing. The same thing is, well, send the data, see whether an ACK has arrived, know how much time to wait for an ACK, decide what to retransmit and when. All of that can be fairly complex, in particular if you have large amounts of data to send, so it might be better to have the operating system do it for us. And the answer is, it is TCP. Why are there packet losses in the internet? Well, we've seen at least one cases which might be transmission errors. Things are not perfect, so even if Ethernet has a error, even if the Ethernet on wired system is in principle very reliable, there might be transmission errors that are not corrected by the Ethernet modulation, and then the Ethernet frame check sequence will detect an error and will drop the packet. This is physical layer errors. They might occur also inside any machine. For example, a router, while copying a packet from one part of the memory to another, might do a mistake and the packet might be dropped. There might be also buffer overflows, which is a completely different reason. If you remember the bridges that we saw last week, I depicted the bridge as a queuing system. Now, a queuing system is very hard in a queuing system to avoid overflow, at least once in a while, because, for example, if in a bridge you have 100 inputs that all go to the same output, and if they're all at the same speed, then the data will accumulate in the output buffer. If that happens once and the buffer has enough space for 100 packets, then nothing will happen. But if that happens continuously because you have 100 data that are streaming at 10 megabit per second to one output port at 10 megabit per second, then there will be losses. Sooner or later, the buffers will die. And as we will see when we discuss congestion control, we should not assume that buffers are infinitely large. It's not a good idea. So error loss may occur, and then TCP has to solve this. TCP therefore guarantees that the data is received without loss. But it does another thing. It guarantees that the data is received in sequence. Something that is not done by UDP, but with UDP the problem was not so important. In UDP, the concept of UDP is message-oriented. If an application sends 2 UDP messages to another one, it is not impossible, though very unlikely, but it's not impossible that the second arrives before the first. There might be, for example, parallel paths on the internet, and one of the IP packets, if the sending is very fast, they're sent practically at the same time, they hit a portion of the internet that's very slow and has parallel paths, then the second packet might be more lucky and arrive before the first. UDP doesn't care, has no means to know that one is sent before the other, or there would be means to know, but doesn't care. So UDP will deliver them as they arrive, in whatever order they arrive. That's the semantics of UDP. It's up to the application to know whether this is before or after. If you're a DNS server, you don't care which one was sent before or after. You just serve requests as they come. If you're doing Skype, you care. So hopefully, if you're using Skype, there is inside the UDP payload something else. In the case of Skype, it's called the Real-Time Transport Protocol, RTP, which is in fact an application layer protocol inside UDP that will put packet sequence numbers inside the UDP payload. In contrast, TCP says no. TCP will deliver to the reading program data in exactly the order that they were written by the source. So if the second block arrives before the first, I will delay it. I will keep it in the operating system buffer and will not make it available. So if the application does a read or a receive from the socket, it might get an answer, sorry, nothing has arrived, even though there is something that has arrived, but it's not in sequence. It will not be made available. So something that is too early is considered not yet available by TCP. I say TCP guarantees that data arrives in sequence and without loss. Of course, this guarantee cannot be perfect. The only guarantee is, in fact, that everything has been done to prevent losses, so you don't need, as an application programmer, to do anything more. But losses are still possible, even with TCP. For example, if you if you cut the Ethernet link between a web server and the rest of the world, if that happens in the middle of a TCP connection, then it's impossible to repair the losses, right? The thing is no longer connected. So there might be losses that are impossible to repair, but anything that is possible to repair it will be done by TCP. So the application hangs, and if it hangs, it knows it is physically impossible to reach the destination. Yes?
Is there a probability that once something is transmitted over TCP, there are still errors in the message because they weren't detected by the error detection method?
So the question is it possible that undetected errors occur, so bit errors, for example, in a packet? The answer is yes, it is possible. We've seen on Ethernet, for example, if you transmit the data over Ethernet and there is 1 or 2 bit errors, with very high probability they will be detected, and this probability is approximately 2 to the power minus 32, so 1 in 4 billions. So 1 in 4 billions might be undetected. Similarly, if you copy data from one piece of the machine to the next, there are similar codes that will repair the errors, but with a probability of the same order. So now, of course, if you're sending one file of a few megabytes to the other side of the world, the probability of that happening, you need first that there was an error, which is rare on most systems, and second, that it is not captured, which is 1 in 4 billions. But if you're Google, that is moving around, shuffling around huge amounts of data at very high speed and 24 hours a day and every day of the year, from time to time you see files that are wrong, that are copied with errors. That happens, yes. So when you do backup, do more than one backup. How does TCP work? Well, it's very simple. If you want to be able to provide data in sequence and detect those that are lost, the idea is, well, you put a number called a sequence number in every TCP packet, which is called a TCP segment. That's part of the TCP header, so it's not put by the user, it's put by the TCP, it's part of the TCP protocol. Then, in order for TCP to work, the two ends that speak TCP open a connection. Open a connection means they synchronize their sequence numbers, and then they send acknowledgements. If missing data is detected, TCP will retransmit. Now there's a bit of complication when to detect that something is missed, when to retransmit, and we'll discuss that in detail now. But here is a first approximation of how TCP works. I'm showing on the left a machine A that is sending data to B and using TCP. So I'm not showing everything, I'm just showing the sequence and acknowledgement number. TCP puts numbers that are not per packet but per byte. It could be per packet. Some protocols similar to TCP put packet numbers, but here TCP put byte numbers. So here, for example, there is a block of 500 bytes that is numbered 8001 to 8500. And when you do Wireshark of TCP, you always see the last number +1, which means the next to be expected. That's the folklore of TCP, so that by doing the difference, you get exactly the number of bytes. So there is a block of 500 bytes, 8001 to 500, in fact. Then when B receives it, TCP will send an acknowledgement. What does that mean, TCP send an acknowledgement? Well, it means that TCP will send an empty packet with one field called the acknowledgement number equal to 8501, which is the last received byte +1. Of course, if B has some data to transmit also, because there is a flow from bidirectional flow from A to B and from B to A, this acknowledgement will be put in the data, in the same packet that contains the data. But here I'm showing a case where only A is sending to B and B does not respond. Even though B does not respond, there will be empty TCP packets that are still 20 bytes of header inside IP packets. Right? So we find this first symptom of using TCP. Even if you download a huge file, 1 gigabyte over a low-speed ADSL line, for example, you can think that the download is one way from the internet to you, but there is a flow of TCP acknowledgements from you to the internet. And sometimes if the uplink is very slow, like it happens on ADSL, in particular if you have low bitrate ADSL, you might be limited by the speed at which you can send acknowledgements. Here, at time 2, A has received the acknowledgement, therefore A is happy and can continue to send. So at time 3, 4, and 5, A sends 3 more blocks of data. It's the TCP at A that sends that. It might not necessarily be the application. It is just TCP has decided to create 3 packets. Now assume 2 of them are lost. Then when the 2 are lost, of course, B receives nothing and does nothing. When the 3rd one arrives, what should B do? Well, TCP says, if you receive something, send an ACK, send an acknowledgement. The acknowledgement that will be received in that case is the largest number received in sequence. So we discover one thing, the semantics of the acknowledgement field in TCP means the largest number received in sequence, +1. So here, because everything that has been received in sequence is up to 8500, TCP will acknowledge 8501. In fact, it has received more. It has received a block here, 9500 to 10,000, but it's not acknowledged, at least not in the acknowledgement field. We will see that it will be acknowledged somewhere else, but not in the acknowledgement field. Now what happens at A? A zillion of things can happen. One of the things that may happen at A is a timeout. When TCP sends a packet, it starts a timer, like in the stop-and-go protocol. After some time, if this packet is not acknowledged, so if the bytes that were sent at time 3 at not acknowledged when the timer expires, then A, the TCP in A, decides this is lost. I will resend. Therefore, it will resend this piece of data here, 800, 500 to 9,000. And now when B receives it, it will ACK the largest number received in sequence, which is now 9,000. Because before we were at 8,500. So we'll receive this. When this is received, then, for example, A might decide to resend the third missing packet. Voila, that is our first glimpse of how TCP operates. After the break that we will do now, we will see more details of this because things are a bit more complicated, in fact. So we do a break.